Thank you, guys. You guys are a very patient audience. I almost expected this session to be half empty now, but awesome. So where I left off was watermarking, and I was talking about how watermarking allows you to control how much late data you want to handle and trade off more state or versus less state to do that. So the other very interesting thing to observe in this API is that this API essentially allows a very clean separation of concerns. For example, when you're working with event time, there are three different things that you may need to specify. There are three different times you need to specify in your query. First of all, is the core thing is the query semantics, and that is specified by the window operation. So what is the window size, etc. And this is essentially a semantics of the streaming of the data frame query, and this semantics is same for batch and streaming. You can apply it on both batch data frame or a streaming data frame. You'll get the exact same semantics, and it defines what the result would be. Whereas the other times that may be present in the query, for example, the watermark time, this is not a streaming query semantics, but it's more like the processing details of how much late data to consider when you're actually running it as a streaming query. For also, if you specify the trigger interval of 10 seconds, that is also processing details that is applicable only when it is actually a streaming query. So this clean separation of concerns is something that you should be aware of when you're actually constructing your query. This is something that is applicable for both batch and streaming, independent of this is just logical semantics. This is something that is the rest of these two are something that is useful only when you're running that logical query as a streaming query on streaming data. There are a few other interesting operations, much more complicated than streaming aggregations, but I will not go into those in this particular talk, because at 4:20 today, I have an additional talk which is essentially a deeper dive into stateful stream processing. It's actually funny that this broad overview is in the technical deep dive session, and my deeper dive about streaming processing is in the normal session. Funny observation. Anyway, so please attend, if you are still patient enough with me, please attend my other talk, which I go into much deeper level details into other stateful operations like this. So one final thing that you always need to do when you're running a streaming application is you want to monitor how your application is performing. So the streaming queries, the object that gets generated when you call start, has a lot of the operations required for processing. For example, you can get the current progress of the streaming query by just calling last progress. And what you get out of it, if you print this last progress object as a JSON format, you get things like what is the current data ingestion rate, what is the current processing rate. If you want to dig deep into what is the latency that the query is seeing, how long is the trigger interval, etc. There is a whole plethora of low-level duration informations on what is taking time. There are details about what offset each of the sources have processed, what offsets each of the sinks have finally committed to. All of those details you can get out of this last progress. Now, this is actually a pull-based API where you can interactively query running streaming query. But if you want to just asynchronously monitor, then there's this API called Streaming Query Listener, where it's basically an interface, a trait, where if you implement your own streaming query listener based on this API, and register your streaming listener into the streaming query, then you can automatically get all these progress events whenever there is progress, whenever a query starts, whenever a query stops because of error, or otherwise, whenever there is progress made into the query because some new data was processed, you will get asynchronous events that you can use to asynchronously monitor your queries. Also, we have integrations into drop wizard metrics. So You can push all of these metrics into Ganglia, Graphite, whatever drop wizard supports, but we have to actually enable this explicitly because it's a lot of data and we didn't want it to enable automatically. So you just have to set this additional configuration to enable the metrics to be written out through the drop wizard interface. And you can look at the Spark documentation on the Spark website to see how to use drop wizard metrics, how to configure Spark to, in general, enable drop wizard metrics. Anyway, so this was a high-level overview of what structured streaming provides. Let me change gears a little bit to actually show you how you can actually build complex apps using these basic APIs. And to explain that, I'll actually use the metric processing system that we have built in our own Databricks. After all, Databricks is a service, it provides a cloud service, and we have to monitor our own clusters, we have to monitor our own services, and so have the same set of problems that many other companies have. So as Michael pointed out, we had built 3 earlier iterations of this log processing pipeline, and each had various degrees of pain points and stuff. And so we learned a lot in that process, and we found that the same set of problems are faced by other companies as well, including our customers. So, and all of that essentially were input into our design process for structured streaming. And so to briefly give a high-level overview of what our log processing pipeline looks like, we wanted to do essentially 4 things. One is basic ETL. We want to collect all the records and store it for fast interactive queries, and from that we want to generate dashboards to see in real time or near real time what is going on in our clusters, in our Spark clusters that we're managing. If there is something goes wrong, we obviously wanted to see alerts that something is going wrong, this cluster is non-responsive, and take actions. And then when things do go wrong, you want to actually do more deeper analysis, ad hoc analysis. So these are all the 4 use cases that we wanted to achieve while designing the 4th iteration of our log pipeline using structured streaming. And this is how we did it. One of the considerations we had earlier is to actually, since this seems like a streaming system, like can we actually build it just using a streaming system like Kafka? Because Kafka had both the stream ingestion part as well as now have the stream processing part. Can we do something using Kafka? And we very quickly realized that this cannot be very well done using a pure streaming framework, because one, streaming frameworks are not designed for very long-term retention, where you may want to, which like something like a file system like S3 or HDF is designed for. So you have to kind of limit how much you're retaining. And the format of the data is not really designed for very fast and efficient querying. So for example, if you are querying by a particular key, which is not the key inside the Kafka, then you have to read all the data inside Kafka to find that one record that you care about. So all the crazy data layout optimizations that databases do cannot be really done inside a pure streaming system, because it's not designed for that. It's not designed for optimized arbitrary reading of files and stuff. And so also, it's not really easy for novice users with the very limited, earlier it was no SQL support, now there's a very limited SQL support in Kafka, but it doesn't have the more complex operations like parsing JSON and stuff and doing it in an efficient manner. It has none of that. So this is what our final 4th iteration of our metric processing pipeline looks like, and I'm going to walk through some of these stages that our data goes through. So the first step is basically collect the data from our Amazon Kinesis pipeline as well as from our Kafka pipeline. These are essentially the raw logs, and parse it and enrich it, clean it up, filter it, etc. So what we have done is essentially build these library of data frames that can be reused. And that is something that we realized while actually, after building the structured streaming APIs within the DataFrame API, when we tried to actually build this, we realized some of the very nice advantages of building it this way is is that you can build a library of these reusable data frames, which essentially represents the exact data, but you can process them downstream in different ways. For example, these are two different data frames that I'm going to reuse over and over again as I build out rest of the pipeline. So this is essentially our raw logs directly from Kafka. And this is our augmented logs where we have taken the raw logs and parsed it from JSON. We have extracted out the timestamp, joined it with our table of customers to add more enriched data. So this is essentially like a stream batch join kind of a thing, resulting in this new data frame, which is augmented data. So now we can do these things like we can directly write out to Parquet. In this case, we use Parquet and Databricks Delta. Since last few months, we have been using Databricks Delta and Parquet combination. And there, we are okay with latencies of the order of minutes. We are dealing with file systems. Anyways, we don't really need lower latency than that. For lower latency stuff, I'm going to come to that in the next few slides. So here we are with this not so low latency requirements. We were earlier repartitioning by 1 because when we were writing to Parquet, now actually we don't do this anymore because we're using Databricks Delta, and Delta takes care of small file problems and stuff. We were triggering by 1 minute and stuff. Now now that the data is in our Databricks Delta tables, what it allows us to do is write all different kinds of dashboards where we can monitor at again, the granularity of minutes to hours. Different dashboards require different things. What is going on in our surveys, in our clusters and stuff. So, it is totally configurable, and some dashboards changes every hour, some dashboards monitors last 10 minutes, so needs to update every minute. So different dashboards can all run on the same Databricks Delta table. For events that actually we need to monitor at even lower latency, what we do is that we have another parallel pipeline which directly reads from Kafka and filters out only the events that we care about. Not all the events, but only the events. In this case, for example, we wanted to monitor the exact state of our clusters to see. So we wanted to filter out just the cluster heartbeats and wanted to do fast alerting on that. So we from the Kafka, we actually pulled out only the events of this type and write it back to Kafka in a different topic, so that now we can do additional alerts on top of that. So we have had simple alerts where we expect very low latency, like 100 millisecond latency, where we want to see that if the cluster is at a very high load, there are spikes. We wanted to highlight those, and then we wrote a PagerDuty sync for that. And I always hope that I am not the one on call. But that's some of simple alerts we have written. We have also written very complex alerts, which is very deep into stateful stream processing, where we are looking at not just the instantaneous load, but what is the history of that cluster? Has it been loaded for quite a while? Things like that. And again, I'll elaborate on map group with state and flat map group with state in my next talk at 4:20 today. And those are much more complex logic, and there we were hoping to get second level latencies, and we achieved that. So both of the simple and complex alerts all from Kafka directly. So there is no file system in the path, which allows us to achieve low latency. And this runs kind of in parallel to the basic ETL pipeline writing into Databricks Delta and Parquet. And so, of course, now that it is in Delta, we can also, besides running dashboards on it, we can also do ad hoc analysis and stuff whenever there is too many warnings and too many errors. So, in short, this whole pipeline that we have built, we are able to run all of this inside the same cluster, same Spark cluster, achieving up to 14 billion records per hour with a size of 10 nodes. And so, and this shows that you can balance different workloads with different latency requirements and throughput requirements all inside the same cluster while ensuring really high performance and throughput. And without the user having to really reason about what goes on when we're running these different workloads in the same cluster. Does one affect the other and stuff? And we've built it in such a way that we have reused all the data frames that we have written. So all the logic to augment the data, enrich the data, etc., just completely reused across all these different, seemingly different streaming applications. All this just reuse them. So as much code reuse as possible. Overall, our customers, we have hundreds of customers running streaming apps in production on Databricks right now, and some of our largest apps, it's a Fortune 100 company that Ali and Michael was talking about, will process tens of trillions of records per month. I think this is an underestimate right now. It's probably more than that. It's growing pretty fast. Anyways, some of the future directions that we are heading towards is continuous processing. So one of the pain points, or one of the complaints that people always had with Spark streaming, or as well as structured streaming, is that we are processing in micro batches. So there's a limit to how low the latency can get. So if you want latencies lower than hundreds of milliseconds, it is hard to achieve that inside Spark. But we were aware of this when we were designing structured streaming, so we designed our structured streaming APIs using DataFrames in such a way that in future, we could actually replace the micro batch engine with a different engine inside Spark that processes data continuously, not as batches. And that is what we are finally doing right now. We're building that engine, and that can provide less than a millisecond latency when you're reading from Kafka and doing some processing and writing out to Kafka. And the cool thing is that if you have a query that that you were running in the current microbatch engine, you don't have to change any of that code. You just say run it on the continuous processing engine if your code is compatible with the engine, and you'll start getting much lower millisecond latency than the microbatch engine. So we have a proposal that is ongoing as a Spark improvement proposal. Please vote on it. Take a look at it if you want to learn more about it. Anyways, I'm close to wrapping up. We have a lot of documentation in the form of both the Scala docs, API docs, as well as detailed blog posts that we keep writing. So do follow us on our Databricks blog, and we do deep dives in each of these components, and it's generally very useful to learn about how structured streaming works at different levels by reading our blog posts. So please, and stay tuned for more blog posts to come. Anyways, to wrap up, one final putting on my Databricks hat, do try Apache Spark in Databricks on our unified analytics platform. We have added a lot more performance optimizations, etc., that is specific to the cloud environment inside our Databricks runtime. So you get significantly better performance and efficiency in using Databricks runtime over Apache Spark. And that's basically it. Thank you very much. We have about 11 minutes for questions, so feel free to shoot. Yep.
Could you actually, here, let me get you. Hi. In the case where there's Kafka broker outage and there's for the consumer and the job is not consuming data for say 1 hour, what happens to those events that come after the hour in terms of the watermark, the high watermark? Are they ignored by the Spark job, or do they get consumed?
So so the question was, to repeat the question, what if there's a Kafka broker outage and you're not getting events from Kafka for about an hour? Yeah. What happens after that, after you restart the query from that hour? So the idea of watermarks is that it progresses only when it gets data, because it's based on the max event time seen by the system. So it progresses only when you are continuously getting data. If your Kafka broker is out and you cannot read from it, then the query just doesn't get any data, so the watermark just stays where it was. So even if it starts getting data an hour later, even if the processing time has proceeded, the event time and the watermark is still exactly where it was an hour ago. So that is the advantage of processing using event time rather than the processing time.
Awesome. So if you have a question, please come up to use this microphone in the center. That would be wonderful. Or I can
question about the partitions, right? So in pre-Spark 2.0, probably, the Spark streaming is pretty based on low-level RDD, so you have corresponding number of partitions where you can consume the Kafka topic. So is it still the same? So if I'm using the structured streaming and get the data frame from the Kafka topic, and what's the number of partitions? It's the same as the number of partitions of the Kafka topic?
Yes.
Right.
So,
okay.
wait, let me elaborate on that. So, yes, by default, the number of partitions by which Spark will read from Kafka is by default the same as the number of partitions in the topic. But there are additional optimizations in our Databricks runtime by which you can specify a larger parallelism than that. So if the bottleneck is not Kafka but something else.
Yeah.
So there are knobs inside Databricks runtime.
So because basically it returns a data frame, so you can apply a number of wide transformation operation on top of that. So this would make the number of partitions of the result data in the frame to 200 partitions by default. So now if I'm going to write that join the result, for example, back to another Kafka topic, and that topic in Kafka is 6 partitions, for example, by default, do I need to call re-partition to make it write to the result to that Kafka
I think that happens seamlessly under the hood.
All right, okay, fine, great, thanks.
Hi. One thing I noticed from a lot of examples that I've looked at for streaming is that the input data seems to always have like a single schema. Do you have any tips for dealing with like heterogeneous kinds of data, where you might have to merge different kinds of data together? Maybe they have common columns that you join on, but they're different schemas.
So something that is a problem that even we have faced in the past in our own pipeline. Some of the tricks that we have done is basically so we are getting data, for example, from Kafka. It's in binary format. What we have done often is basically split it up into 2 different schemas, parse out the JSON in 2 different schemas, and then kind of unify back them together into a common schema, and then proceed it forward. So yes, you have to do some schema magic to kind of unify the schema across the various different schemas that may exist in the data. So that is something you have to do it explicitly.
Hi. So instead of completely dropping the events that are past the watermark, how complicated would it be to possibly add, say, an extra column that's almost always empty, except when there are these super delayed events for really deep forensics, for example, in the future?
So it depends on what sort of query you're running. So the whole point of Watermark is that if you're doing stateful processing, you want to limit the state. In this case, keeping around I feel that the kind of query that you talked about, where you want to keep the late data around, you want the raw late data around, except tagged that this was later than a certain point. So that is essentially not an aggregation kind of query. That's more like a map only ETL kind of thing, right? So there, the watermark, etc., doesn't matter. Even if the data is late, it will just be put into the right partition inside Parquet and stuff. And so there, just specifying the watermark does not eliminate the late data. It's only when you specify the watermark and you're doing some sort of stateful operation, that's when the late data that is beyond the watermark will be ignored and stuff.
Okay, cool.
So this does not make a difference when you're not doing any stateful, if you're doing something like map only kind of stuff.
Yeah, thanks.
Maybe one from this side. I think this side is starving.
Can you basically take the late data that would be ignored in the stateful job and like kick that onto like a dead letter queue or something? Is there some kind of callback that you can use to work with that data for downstream?
Not right now, but that is a request that has cropped up multiple times. That is something that is on our wish list of stuff that we would like to have in our APIs.
Kind of related to a lot of what people have just been talking about, the whole watermark thing. It seems like for some types of output of the processing, you might then be able to pull it back from, let's say, a table in. So where the state's fallen off the bottom of the watermarking, is there any kind of idea? Could there in the future be any kind of idea of pulling that state back from long-term storage, say for instance a table, through some sort of use-defined method?
Yes. So that is where our arbitrary stateful processing operator map group with state comes in, where you can do arbitrary stuff that you want, completely arbitrary stuff. And this is something I think it's best if you come to my talk, and that would give additional context to dig deeper into your particular use case.
Thank you.
Please come to my talk. Shameless plugging.
So you showed that you can define custom event times, but can you also define custom processing times, like the timestamp it's tagged in Kafka, like the newer versions do? So that you can have consistent allowed lateness when you reprocess data, in fact.
So let me make this clear. So all these APIs, whenever I'm calling it event time, it's just a timestamp column. You can use any column as a timestamp column. That column can be a timestamp column inside the JSON, or it can be the timestamp column that Kafka provides, or it can be the timestamp column which has the current processing time. There's a function called current timestamp, which just puts in the current processing time. So that timestamp can be any column. And based on the semantics of what that column has, you will get the application level semantics that you desire.
Yes, but so I understand that, and I would like that to be the event business time. But then at the same time, I would like to leverage the concept of allowed lateness to match it with the time where it arrives in Kafka, not necessarily the time at which it gets processed in Spark. Because I do continuous reprocessing, in fact.
So then just use the Kafka's timestamp. So so when we create a data frame from the Kafka source, it returns the Kafka timestamp. You can just use that.
Okay,
that's it.
Thank you.
Hi. So you kind of showed that you can read in Spark from multiple Kafka topics kind of together. So what methods are available to kind of combine those topics together into a single kind of data frame, as opposed to like reading, having multiple streams reading from multiple topics?
You can. So there are multiple different ways. For example, when you're creating a Kafka source data frame, you can just say subscribe a comma-separated list of topics or a topic pattern, or if you want more and that would essentially return a common data frame which has all the data from all the topics, because the schema is common, because all you get is essentially key value binary columns.
Right.
If you want to do something like for different topics, do different sort of cleanup and then unify them to write it out to a common table or something,
right,
or a common downstream topic, then you can create different source data frames, do the processing, put them in the same schema, and then call union on them.
Right.
And then do further writes out.
Okay.
So both are possible.
Right. Okay. Thanks.
Hi. If you have Avro data in a Kafka stream, and getting that into a data frame, is there any like out of the box serialization, deserialization?
We are working on it.
Do you know when that might be ready?
No promises, but we're hoping that Spark 2.3 has something like that.
Awesome.
We're hoping. But this is one of the things that has been requested over the last 1 year multiple times. So it has been in our wish list for a while, and now it has bubbled up.
Great.
So maybe the dead letter queue will also bubble up at some point. We're hoping. It all boils down to the amount of resources we have.
Hi. It was talking about put the data in real time into a Parquet file. How does the update with the late data works on that? Because you need to rewrite all the partition on the file if it's...
I didn't go into too much detail about this, but if you choose a file sync, then the only mode you're allowed to put the whole query in is an append mode. Because with Parquet, with just bare bones Parquet files, we don't support updating a Parquet file and stuff. So now the query has to be in append mode, and there are restrictions on what operations can be done in append mode. For example, if you're just doing a streaming aggregation, there any of the grouping key value can change, etc. So that you cannot put into an append mode. But for an aggregation on a window with watermark, you can put that in append mode because we can output only the final count when it has crossed the watermark. The final count can be outputted in an append mode into a Parquet file. So there are restrictions on what modes are allowed based on the correctness of the operations.
Okay, like the watermark would be your partition key, something like that.
Sorry, could you?
Like the watermark timestamp could be the partition key for the file.
Yes. So if you are doing something like a pure map-only stuff that is going to be in append mode, then and if there is late data, then actually the watermark doesn't matter. If there is any data that is late, it will just be written to an older partition. That's it. So their watermarking etc. doesn't really matter because there is nothing stateful about it.
Okay, thank you.
Awesome. I'm going to have to cut us off right here. Unfortunately, we don't have any more time for questions right now, but we can definitely find TD after.
Miles, hold on. So I have, so I'll be at the Databricks booth from till 2 o'clock. So feel free to come at the Databricks booth over lunch or after that to talk to me for more questions.
Awesome. Let's thank TD one last time for his talk.
Thank you very much. You have been a wonderfully patient audience.